155 years ago, on the 11th of December 1867, physicist James Clerk Maxwell wrote a letter to his friend, Peter Guthrie Tait. In this letter, he explained a thought experiment involving a clever little demon, which is able to extract useful energy out of thin air. Maxwell's demon has haunted the foundations of thermodynamics ever since. Hi, I'm Maria. Welcome back to my video series where I explain quantum paradoxes using quantum circuits. Today I'm going to explain the Maxwell's demon thought experiment, which was originally proposed as a paradox for classical physics. I'm going to explain a microscopic version of the thought experiment called Szilard's engine, and how you can code a quantum Szilard engine as a quantum circuit using Qiskit. Along the way, you'll find out why I think that Maxwell's demon is one of the most simple yet controversial thought experiments in all of physics. I'll start by explaining the classic Maxwell's demon thought experiment. The thought experiment starts off with lots of particles randomly moving around in a box. I'm going to represent these particles by these little chocolate pumpkins. And the demon is in control of a trapdoor, which is in a wall in the middle of the box. So the demon is able to open and shut the trapdoor to decide whether a particle can move from one side of the box to the other. So as the particles are randomly moving around, the demon decides to open the door to let fast particles in to the right, and to open the door to let slow particles in to the left, until all of the fast particles end up on the right and the slow particles on the left. So then the right side of the box has the fast moving particles, and so it's hot, and the left side of the box has the slow moving particles and is cold. The demon has managed to separate the particles in the box into a hot side and a cold side, which you could then use to extract useful energy. For example, we could put a turbine in the middle of the box and use the difference between the hot side and cold side to turn the turbine to drive an electricity generator to charge up your phone. It looks like the demon can extract useful energy out of the random motion of the air. So why aren't we all charging our phones from the air? The second law of thermodynamics says that this is impossible. The random motion of the air is called heat, and the useful energy we need to charge our phones is called work. The second law says that it's possible to turn work entirely into heat, but impossible to turn heat entirely into work. Another way of explaining the second law of thermodynamics is in terms of entropy. Entropy is a measure of disorder, and a system has higher entropy if there's more possible states that the system can be in. For example, an egg begins as a yolk and a white. This is a very highly ordered, low entropy state because there's only a few ways that the egg particles can be arranged for them to be separated into the yolk and the white. As I beat the egg, I'm increasing its entropy and it's becoming more and more mixed. This is because there's lots more ways for the egg particles to be arranged so that they're mixed together than so that they're separated as a yolk and a white. The second law of thermodynamics says that the entropy of any isolated system is very unlikely to decrease. So even if I keep beating this egg, it's very unlikely to go back to being a yolk and a white. The fact that we only go from order to disorder is what gives time its irreversible forwards direction. But Maxwell's demon seems to be able to decrease the entropy of the box, because having the fast particles separated from the slow particles is a lower entropy state than when all the particles were randomly moving around. At first, scientists thought that the resolution to the paradox was that for the daemon to obtain information about whether the particles are moving fast or slow, it needs to measure them, and this measurement has some minimum entropy cost. But in 1981, IBM researcher Charles Bennett proved that this was wrong. You can measure the information about the particles with no entropy cost. The daemon needs to store information about the particles in its memory. We could think of the memory of the daemon as being like these chocolate coins. So all of the memory coins of the daemon start off in the same state. So we could say they all start off as heads. And then as the daemon measures the states of the particles, it uses the coin to store the information about whether the particle is moving fast or slow. So if it's moving fast, then it leaves it as heads, and if it's moving slow, then it's flipped to tails. So after a while, all of the memory of the daemon will be used up with information about the particles. Now, in 1961, another IBM researcher, Rolf Landauer, showed that erasing information has a minimum entropy cost. So if you have a coin which could be heads or tails and you want to reset it back to heads, then that will cause a minimum entropy increase to the environment. This means that as your computer is erasing information, this will cause the room to heat up by a tiny amount, so small that you would only notice it in very carefully controlled experiments. This is known as Landauer's principle, and Bennett argued that erasing the information in the daemon's memory would increase the entropy of the environment by just enough to save the second law of thermodynamics. So the overall entropy hasn't decreased, and there is no paradox. Now I will explain the single particle version of Maxwell's daemon, which is called Szilard's engine, and then I'll show you how to code a quantum Szilard engine using Qiskit. So in Szilard's engine, there is a single particle randomly moving around in a box. And so it has equal chance of being on the left side of the box and the right. Then the daemon measures which side of the box the particle is on and stores this information in its memory. Then if the daemon saw that the particle was on the left, it inserts a partition in the middle of the box and attaches a weight on the left side. And then as the particle collides with the partition and expands to fill the whole box again, this pulls up the weight and extracts useful energy. Now, if the daemon had instead put the weight on the wrong side of the box, then the particle expanding into the box would have lowered the weight and we would have lost useful energy. If the daemon measures the particle to be instead on the right and then attaches the weight on the right side, then again the weight will lift up and the daemon can extract useful energy. So if the daemon correctly places the weight, and then it will always lift up, but the daemon's memory needs to be reset in order to repeat the cycle. And according to Landauer's principle, erasing the daemon's memory has a minimum entropy cost to the environment, and this is what compensates for the useful energy we got out by lifting the weights. So how can we represent these different parts of the Szilard engine cycle using a quantum circuit? I'm going to do this by presenting the particle, memory, and weight using qubits. So the particle starts off randomly moving in the box. So I'll introduce a qubit for the particle, and what I'm going to do is have this qubit start off in a maximally mixed state. Maximally mixed states are what you get if you flip a coin to decide whether to prepare your qubit as a 0 or a 1. So it's the most random state possible. It's different to a superposition state of 0 and 1. Next, I'm going to have one qubit as the memory qubit, and this is going to start off in the 0 state, which is the blank memory of the daemon. Finally, I need some qubits to represent the weight. Now, I need the weight to be able to be lifted or to be lowered. So it needs to have at least 3 different states. So I'm going to represent it using 2 qubits, where the state 0, 0 is the lowest energy state of the weight, 1, 1 is the highest energy, and 0, 1 and 1, 0 are in the middle. So here I've introduced my single qubit for the particle, single qubit for the memory, and 2 qubits for the weight. And then I'm going to create a quantum circuit with all of these qubits called engine. And here I've got a classical register of 2 bits, which I'm going to use to check at the end whether the weight was lifted or not. So we can start preparing this circuit by initializing all these particle memory and weight qubits in the correct states. So for the particle, I've added an identity gate, which looks like it's not doing anything. But this is because I'm going to use a noise model in Qiskit to add noise to the identity gate, which is going to prepare the qubit in a maximally mixed state. This is what noise in qubits generally does. It randomizes the state of a qubit, and then they end up maximally mixed if they've had lots of random noise applied to them. And I also need to prepare my weight in the middle energy state because it starts off not lifted or lowered. And so I'm going to start it off in the state 0, 1 by applying an X gate to one of the weight qubits. So now that we've prepared our qubits, we can start doing the steps of the Szilard engine cycle. So the first step is that the daemon measures the state of the particle. So we're going to represent this in the circuit by a control NOT gate between the particle qubit and the memory qubit. So if the particle is a 0, then the memory is left as a 0. If the particle is 1, then the memory qubit is flipped to a 1 because the NOT gate is applied. So this corresponds to if the particle is on the left, then the memory stores information that it's on the left and it stays as 0. If the particle is on the right, the memory stores information that the particle is on the right and the qubit is flipped to 1. So that's the measurement step. So now let's work out what happens in the work extraction step. So if the particle and memory are both 0 or both 1, then that means that the daemon has correctly measured where the particle is and it can apply the weight in the correct direction to lift it. Now with our qubits, lifting the weight is the same as adding an X gate to the first weight qubit, so that overall it goes from the state 0, 1 to the high energy state 1, 1. But if the particle and memory states are different, then that means that the memory is wrong about where the particle is and the weight will be attached on the wrong side. So then the weight will be lowered to the low energy state, and so our weight qubits are going to go from 0, 1 to 0, 0, which you can do by adding a NOT gate to the 4th qubit, which is the second weight qubit. Now you can simplify this logic of what happens to the weight qubits depending on the particle qubits using the gates that I've shown here. So we have a series of C0 gates and X gates, and if you check what happens when you put 0, 0 and 1, 1 as an input, you'll find that the X gate is always applied to the weight in order to lift it, and if the inputs are 1, 0 or 0, 1, then the X gate is always applied to the second weight qubit to lower the weight. Now, after the weight has been lifted, the particle ends up being randomly moving around in the box again. So we need to make sure that the particle ends up not correlated with the memory of the daemon or with the weights after this work extraction step. So what I've done in the circuit is add another identity gate, which is going to be noisy when I add in my noise model to randomize the state of the particle and make sure that it's not entangled at all with the memory and weight qubits. So after doing all this, we end up with the memory being used up. So what actually happens is the memory has ended up in a maximally mixed state, and to repeat the cycle, we need to reset it to the 0 state. So what I've done is add in the reset gate. Well, it's a reset operation because it's a non-unitary operation. And this resets the memory state back to 0 so that the memory is ready to repeat the cycle. So here I've added measurements in to the weights so we can find out whether the weight is successfully lifted by our daemon. In order to run this circuit, I first need to create the noise model, which is going to add the noise to the identity gates. Here I'm using a noise model with the depolarizing error, which takes you from a state to a maximally mixed state, which is what we want. And you can see when I print out the noise model that the noise will be added to the identity gate. So now I can run the circuit and see what happens to the weights. So we can see that the output of the weights is 1, 1. So our weights have been successfully lifted to the high energy state. So now let's check what states the particle and memory have ended up in. If we check the state of the particle by adding a measurement to the particle instead, then we see it has equal chance of 0 and 1, which is what we expect if the particle has ended up maximally mixed again, ready for the next round of the cycle. And now we can check the memory state, and we see that it's always 0. So our reset operation of erasing the memory to 0 has worked. So in our circuit, we added a reset operation to return the memory to the 0 state. And this is what has a minimum entropy cost on the environment. But what would happen if we didn't do that reset and try to get away with reusing the memory without returning it to a blank state? Well, we can try it by starting off our memory qubit as a maximally mixed state. So what I've done here is I've added in an identity gate, which is going to be noisy, to the beginning of the memory qubit, and then we can run it to see what happens to the weights at the end of the circuit. And what we see is that now, instead of the weight always being lifted, half the time the weight is lifted, ending up as 1, 1, and half the time it's lowered, ending up as 0, 0. So we have lost work just as many times as we have gained work. So if you try and escape the second law by not resetting the memory, then all you'll get is half the time you'll get the work, but half the time you'll lose it. So why does resetting the qubit state have an entropy cost? We can understand this by, instead of using the Qiskit reset operation, actually seeing what's happening when we do the reset using a quantum gate. So what I've done here is I've created a 2-qubit circuit with a qubit to represent the environment and a qubit to represent the memory. And we have the noisy identity gate to start the memory off in a maximally mixed state. Then to reset it, I've introduced a swap gate between the environment and the memory, so the memory ends up in the 0 state and the environment ends up maximally mixed. So we can see that for the memory to go from being maximally mixed to 0, the environment needs to go from 0 to maximally mixed. Now, we measure entropy of quantum systems using something called the von Neumann entropy. And it turns out that the von Neumann entropy of the 0 state is 0, whereas the von Neumann entropy of a maximally mixed state is not. So the environment's entropy has increased, and that's the price we pay for erasing the memory of the qubit, of the memory qubit, and resetting it to 0. And we can see by running this circuit that we end up with the memory being in the fixed 0 state and the environment being randomly 0 or 1 at the end of the circuit. Now, the use of Landauer's principle to exorcise Maxwell's demon and save the second law of thermodynamics continues to be contested. Some people argue that tasks like erasing information don't necessarily need to increase the entropy of the environment. Others say that using Landauer's principle to save the second law in the Maxwell's demon paradox is circular, because the principle itself was originally derived using the second law. Lots of these arguments come down to people disagreeing about what Landauer's principle actually is in the first place. Meanwhile, other researchers have been investigating whether Landauer's entropy cost is the only price we need to pay to run an engine using Maxwell's demon. For example, it may be that if we erase information faster, we need to pay a higher entropy cost. Maxwell's demon has been causing chaos since 1867, and recently it has been trying its hand at messing with quantum technologies. We can implement a version of the thought experiment using a simple quantum circuit in Qiskit, and we see that there is no paradox after all. The power that the demon gained by measuring information about a qubit state is balanced by the entropy increase of the environment needed to erase the demon's memory. Let us know in the comments if you think that Maxwell's demon has been exorcised for good, or if it will be back to haunt thermodynamics with tricks and treats for many years to come.